Okay, so I'm not sure if you noticed, this is my second attempt at recording this lecture. I recorded the entire thing without sound because I neglected to check that the microphone was on. You know, these things happen. Anyways, I apologize for that. I wanted to say about the interactive lecture on Monday. In the first two interactive lectures at 10 and 11 a.m., I was trying to get people to read their own work, and I really think that is a good thing to do. And, you know, in the humanities, professors actually force you to do that, but I guess I think it's better for a math class to have a more relaxed and fluid type of discussion where students just ask questions about various aspects of the homework and lecture material, and you can, just kind of ask me things without having to put forward anything of your own work. Okay, so that was the model I tried to implement in the 4 p.m. lecture on this past Monday, and I'll try to implement I'll try to implement this more relaxed, free-flowing model in all of the interactive lectures going forward. Okay, so this lecture is about a concept called conditional probability. So, conditional probability is a way of incorporating the following epistemological process into mathematical structure. It asks, if I already know that event A is going to happen, how should I update my beliefs about event B? And by update my beliefs, it means that you want to take the event A as given and calculate a new probability for the event B that reflects not the a priori probability that B happens, but rather the conditional probability that B happens, given that A is already assumed to occur. And that probability is a real number, just like every other probability. And probabilities are numbers between 0 and 1. That's what the unit interval axiom says. And so what we need to do to incorporate this type of question into our mathematical theory is to figure out a way to assign numbers between 0 and 1 to events that are conditional or contingent on another event A. And so the basic idea by which we want to do this is to replace the original sample space, which contains every possible outcome, with the actually, let me change this notation a bit. We want to replace the sample space which contains every possible outcome with this smaller sample space which just consists of the event A. And so we're going to replace our original sample space with a new sample space which is just the event A. And we're going to replace the event B that we're interested in with the event B and A. So we're going to replace the event B with the event B and A, which consists of all the outcomes which fall under our condition of interest B that are consistent with the hypothesis that the event A has already happened or is certain to happen. And in order to get the unit interval axiom and the axiom of certainty to work out properly, we need to think of the procedure of replacing the whole sample space with A as incorporating a mathematical procedure where we replace 1 with the probability of A. So instead of having the probability of B divided by the probability of the whole sample space, which is just the probability of B divided by 1, which is the probability of B, we're going to look at what's highlighted in the teal formula. The probability of B and A divided by the probability of A. And this formula is what we'll call conditional probability of B on A, or the probability of B given A, or maybe just for short, the probability of B bar A, but we're going to use this little notation, B bar A, for the event, the probability of B conditioned on A. So it's really important to remember that there's no such event as B conditioned on A. It's like we're not taking the probability of a new event B bar A. That's not what this notation means. There's no event B bar A that corresponds to what's inside the probability symbol here. Instead, it's a different concept where we're calculating a new notion of probability that satisfies all of the axioms of probability, just like we would if we didn't have the bar with A. And so what we can check is that this satisfies literally all of the axioms of probability. For example, we can say that if we have two mutually exclusive events, then the conditional probability of the disjunction is the sum of the individual conditional probabilities. So this would be what's called the additivity axiom for mutually exclusive, or this would be called the conditional additivity axiom for mutually exclusive events. At least this is the simplest case of it. So the important, I try to do the lecture notes so that the most important things to remember are highlighted in teal, and the most important thing to remember here is the conditional probability formula. But more generally, you can remember that the conditional probability works exactly like a normal probability, where you've made certain conceptual substitutions. For example, we've replaced the whole sample space with A. We've replaced 1 with the probability of A. We've replaced B with B and A. We've replaced normal probability with conditional probability on A. And all of the normal things we know about probability also apply to conditional probability, including the conditional additivity axiom for mutually exclusive events. So one thing that's important to do when you're building a mathematical theory is to kind of go through what we call sanity checks, where you look at especially simple cases. Someone's emailing me giving me their condolences on the fact that I'm literally redoing the lecture right now. But yeah, anyways, these things happen. It's ultimately my fault for not checking the microphone was on. But yeah, anyways, basically, so it's important to do sanity checks where you take particularly simple cases of what you just defined and see if they agree with what you're trying to build in your theory. So if we think about conditional probability where we're conditioning on the entire sample space, so conditional probability of B given omega, what are we saying? We're saying that I know something certain is going to happen. How should I update my beliefs? So it's like, I know that 1 + 1 is 2. What should I do about my probability given that knowledge? And if you think about it intuitively, the answer is nothing. You shouldn't change your ideas about probability at all, given your knowledge that some kind of certain or tautological thing is going to happen. Just saying that 1 + 1 = 2 can't possibly give you any new information about probability, because you already knew that before you even set up the experiment. So if we're conditioning on a certain event, so we're conditioning on the whole sample space, it stands to reason that this should just work out to exactly the same concept of probability as we had before without any kind of conditioning. And you can see, all right, so if you look at B and the whole sample space, that's just the event B back again, because B and something certain is the same condition as B, and B is already a subset of the sample space. It already implies a tautologous condition, so taking the conjunction with the tautologous condition or taking the intersection with the entire sample space doesn't change the event B. So probability of B and sample space is the same as the probability of B. And then the axiom of certainty says the probability of A turns into the probability of sample space turns into 1. So we do recover the normal concept of probability as what you get by conditioning uncertainty. And another important sanity check is thinking, okay, what about conditioning on impossibility? What happens if I condition on an impossible event where the probability is 0? And if you think about that, your brain should explode, because you're like, that makes no sense at all. Saying, I already know that something impossible is going to happen. So I already know that 1 plus 1 is 3. How should I update my beliefs about probability? Well, you know, in math, you're not allowed to start a sentence with, I already know that 1 plus 1 is 3. And so what we should do is say that conditioning on an impossible event just doesn't make any sense. You can't talk about the probability of B given A if A is impossible, because, you know, you can't assume something impossible happens and then start deducing consequences, because that makes no sense. And that's reflected in our mathematical theory with the universal consensus that division by 0 is a terrible idea. And if you try and condition on an impossible event, our mathematical theory forces you to divide by 0, and, you know, we don't like to do that. If you ever have a friend who's a physicist or an astronomer, annoy them by asking them to explain the concept of a black hole without invoking division by 0. But anyways, in math we don't divide by 0, and so the idea that it's nonsensical to assume an impossible event happens is reflected by the fact that conditioning on an impossible event forces you to divide by 0 in the formula for conditional probability. Okay, so let's look at some examples with conditional probability. So let's say we're flipping 3 fair coins. What is the conditional probability of 2 out of 3 heads, given that the first flip is heads? So the initial thing we want to look at here is the word fair, which tells us that, okay, we're dealing with a uniform probability space. So this means we're going to have 8 possible outcomes, and each of them is going to have probability 1/8. We can also deduce that by applying the principle of successive experiment 3 times to the event of flipping a single coin once, where you're multiplying 2 by 2 by 2 is 8. Okay, so the first thing to do, like always, is to translate the problem into mathematical language. And what we're going to do is we're going to define an event where the first flip is heads. We'll call that A. Then we'll define an event where 2 out of the 3 flips are heads, and we'll call that B. And what we're doing is we're looking for the conditional probability of B given A. So because this is the very first example we're doing with conditional probability, we can approach it by listing out the entire sample space because it's so simple. So we can just list out these 8 outcomes, and I've marked the outcomes which fall in the event A in blue, and I've marked the outcomes which fall in the event B in green. And so we can see the conjunction is the 3 outcomes in orange. And so we can use our uniform probability formula. Well, technically the uniform probability for A would come out to be 4 outcomes in A over 8 outcomes in total. So 4 over 8 is a half. And then for A and B, we can say, all right, we have 3 outcomes in A and B over 8 outcomes in total. So that's going to get us the probability of A and B is 3 over 8. And so now we can say, well, let's do the conditional probability formula. So probability of A and B over probability of A, so 3 over 8 over a half. It comes out to be 3/4, which is 0.075. Or sorry, 0.75. So anyways, you can see in this case what's going to happen again and again, which is that our theory of normalizing by dividing with the probability of A means that conditional probabilities always come out to be scaled appropriately in the unit interval, like the axiom asserts. And so you can think of this in terms of just kind of restricting the sample space to the 4 outcomes that start with H, and looking at, oh, I have a sample space with 4 outcomes, and I have 3 of those which are 2 heads, so I have 3/4 is the conditional probability. Okay, so we can see a slightly more complicated example of conditional probability. Let's say we have this example where we have a 40% chance it snows tomorrow and a 40% chance it rains tomorrow. And we're being asked, if I know it does not rain tomorrow, what is the conditional probability it snows, assuming only one can occur? All right, so we need to translate this into mathematical language. And what I would suggest to do is to look at the fact that we're being asked about the probability that something does not happen. So, since we're being asked that the probability about something does not happen, we probably want to work the concept of the complement of an event into this problem. So let's define A is the event it rains tomorrow, and B is the event it snows tomorrow. And so we can say, all right, what we're being asked about is the probability of B conditioned on A complement. The probability it snows tomorrow given that it does not rain tomorrow. So let's go about trying to figure this out. So the probability of A complement, we know by our basic formula, is 1 minus the probability of A. So there's a 40% chance it rains tomorrow. So 1 minus 4 over 10 is 6 over 10. So the probability of A complement is 6 over 10. And so now let's try and think about the probability it snows tomorrow. So how are we going to figure out the probability it snows tomorrow? Well, what we're going to do, or how are we going to figure out the probability it snows tomorrow given that it rains tomorrow? We're going to need the probability it snows tomorrow and it does not rain tomorrow, because the top of the conditional probability formula requires us to look at the probability it snows tomorrow and does not rain tomorrow. So we need the probability of B and A complement. And a good trick we can use here is what's written at the bottom of the page, which is that if you have events and C implies D, then you can conclude that the probability of C and D is equal to the probability of C. And the way to think about that is, if I know that C automatically implies D, then the likelihood that C happens together with D is just the same as the likelihood of C, because no matter when, C happening together with D is something we already knew in advance. We knew that C implies D. So the likelihood of C happening together with D is the same as the likelihood of C if C implies D. So using that trick, we can say, all right, the question tells us that the probability it rains tomorrow, or the event it rains tomorrow, is exclusive with the event it snows. So the event it snows implies that it does not rain. So since the event that it snows implies that it does not rain, we can say the probability of B and A complement is the probability of B, which is 4 over 10. All right, and so now we can calculate the probability of B given A complement using the conditional probability formula. Probability of B and A complement over the probability of A complement. So 4 over 10 over 6 over 10 gives us 2/3, which is 0.666. the most heavy metal of probabilities. Okay. So the concept of conditional probability starts to get really important and useful when you use it as a tool to calculate things you aren't able to calculate without knowing conditional probabilities. So the basic way to use conditional probabilities in calculations is what's called the Tower rule. So this concept has a lot of names. I'm calling it the Tower rule because I like to think of it as a tower of conditional probabilities. You might hear it called the multiplication rule for conditional probabilities or the chain rule for conditional probabilities. But it has a variety of versions depending on how many events you want to apply it to. So the simplest version of the Tower rule is just applies to two events, and I have it highlighted in teal at the top of the page. So it allows you to calculate the probability of A and B as the probability of A times the probability of B given A. And you can see this calculation just works out as canceling out the probability of A. Then you have another version of the Tower rule where you're applying it to three events. And you're saying, well, the probability of A and B and C, I'm going to calculate as the probability of A times the probability of B given A times the probability of C given B and A. And you can again verify this using a kind of cancellation, which in this case starts to look like the beginning of a telescoping product. And then at the bottom of the page, I have the most general form of the Tower rule for conditional probabilities, where you have an arbitrary finite conjunction of events, and you're saying the probability of this A1 and A2 and A3 up to AN is the probability of A1 times the probability of A2 given A1 times the probability of A3 given A2 and A1 times the probability of A4 given A3 and A2 and A1. And you keep taking the conditional probability of the next event given the conjunction of all the previous ones in the list. And you multiply those together, and you get this way of calculating the probability of a conjunction using knowledge about probabilities of using knowledge about conditional probabilities. And when you have this general form of the Tower rule for conditional probabilities, it really does work out as an exact telescoping product, and you can see it's just a lengthier version of the two things on the top of the page. So the Tower rule is a very important way to get from conditional probability to absolute probability. It can also be used to calculate conditional probabilities given absolute probabilities. For example, if you look at the middle thing, you can imagine rearranging it to get a formula for the probability of B given A as the probability of A and B and C divided by the probability of A times the probability of C given B and A. So you can rearrange these formulas in all kinds of ways. And, you don't have to worry about dividing by 0 because, well, just, avoid dividing by 0 and make sure that all the events you're conditioning on have positive probability. Okay. So we can see an example of how to use conditional probability to calculate a probability of a conjunction. So let's say we have an urn being chosen fairly at random from 2 urns. And the first urn contains 30% red spheres and 70% blue spheres. And the second urn has all purple spheres. So we want to know what is the probability of drawing a red sphere from this process. So we can see that the word fairly clues us in to tell that we have a 1/2 probability split between the 2 urns. And what we're asked to do is calculate the probability of drawing a red sphere. But because the second urn has all purple spheres, we can use the trick I talked about before, which is super useful in conjunction with conditional probability, to say that, okay, if I start my translation to mathematical language by saying that the event A is urn 1 being chosen and the event B being a red sphere drawn, then B implies A because all of the red spheres are in the first urn, and therefore the probability of B is the probability of A conjunction B. So I can start trying to use my conditional probabilities by calculating the probability of A and B. So the probability of A, I know, is supposed to be 1/2 because it involves a fair choice between 2 urns. And the probability of B conditioned on A is 3/10 because the first urn has 30% red spheres, so I have a 3/10 probability of drawing a red sphere given that I chose the first urn. And so now we can say, all right, I'm going to use the simple case of the tower rule for 2 events to say that the probability of A and B is the probability of A times the probability of B given A, which is 1/2 times 3/10, which is 3/20, which is 0.15. And because I have this trick where B implies A entails that the probability of B equals the probability of A and B, this 0.15 is the correct answer for the probability of B. Okay. So let's have a look at a slightly more complicated example of how to use the tower rule. So let's say a deck of 52 cards is dealt fairly to 4 players. So the word fairly here means that we have 52 choose 13, 13, 13, 13 outcomes, which are divisions of 52 cards into 4 hands of 13 for 4 different players, and all of those various divisions are equally likely. And so we're asked to compute the probability that each player has exactly 1 ace. Okay, so what we want to do here is to compute the probability that all the aces are in different hands. And what the strategy we'll use is we'll start by computing the probability that the ace of hearts and the ace of spades are in different hands. And then we'll compute the probability that the ace of hearts, ace of spades, and ace of diamonds are in different hands, given that the ace of hearts and ace of spades are in different hands. And then we'll compute the probability that all aces are in different hands as the probability from the tower rule by calculating the probability that all aces are in different hands, given that the ace of hearts, spades, and diamonds are in different hands. So the idea here is that we're going to use the tower rule as its metaphorical name suggests and try and climb up to a solution by using the tower rule as a step-by-step kind of process to get from easier things to more difficult insights. So the first thing we want to do, let's calculate the probability that the ace of hearts and ace of spades are in different hands. Okay, so one way we can do that is to say, what's the probability the ace of hearts and ace of spades are in the same hand? Well, no matter what the probability of, or no matter what hand the ace of hearts is in, there's 12 other spots in the hand that contains the ace of hearts, and each one of them has a 1/51 probability of being filled with the ace of spades, because there's 51 over other cards, and the ace of spades is one among the 51 that aren't the ace of hearts. So in the hand that contains the ace of hearts, there's 12 other spots, and each of those other spots has a 1 over 51 probability of being filled with the ace of spades. So the probability that the ace of spades is in the same hand as the ace of hearts is 12 over 51, and the probability of the ace of hearts being in a different hand from the ace of spades is 1 minus 12 over 51, which is 39 over 51. Okay, so now let's assume that the ace of hearts and the ace of spades are in different hands. Okay, so what's the probability that the ace of diamonds lands in the same hand as the ace of hearts? Well, there's 12 spots in the hand that contains the ace of hearts, and there's 50 cards other than the ace of hearts and the ace of spades, of which the ace of diamonds is one. So each of the 12 other spots in the hand that contains the ace of hearts has a 1 over 50 chance of being filled with the ace of diamonds. So there's a 12 over 50 chance that the ace of diamonds gets put in the same hand as the ace of hearts. And now, given that the ace of spades is in a different hand than the ace of hearts, we can use exactly the same reasoning to say that there's a 12 over 50 chance that the ace of diamonds gets put in the same hand as the ace of spades. And then from that, we can conclude that the chance the ace of hearts and the ace of spades and the ace of diamonds are all in different hands is 1 minus 24 over 50, which is 26 over 50. Okay, then we need to perform the same reasoning process for a third time. We're going to assume that A2 and A1 hold because the ace of hearts, spades, and diamonds are in different hands. Now, what's the probability the ace of clubs gets put in the same hand as the ace of hearts? Well, there's 12 other spots in the hand with the ace of hearts and 49 cards, including the ace of clubs, other than the 3 aces that have been previously distributed. So there's 12 spots for the ace of clubs in the hand with the ace of hearts, and it has a 1 over 49 chance of filling each of them. So we can reason as before and add up these 3 probabilities. 12 over 49 plus 12 over 49 plus 12 over 49 is 36 over 49, which is the probability that the ace of clubs gets put in the same hand as one of the other aces, assuming the other 3 aces are in different hands. And so the probability of that is, with the probability of all aces being in different hands, assuming that 3 aces are in different hands, is 13 over 49. Okay, so what have we computed? We've computed the probability that the ace of hearts and the ace of spades are in different hands is 39 over 51. We've computed that given the ace of hearts and spades are in different hands, the ace of hearts, spades, and diamonds being different hands is 26 over 50. And we've computed that given the ace of hearts, spades, and diamonds are in different hands, all aces being in different hands has a probability of 13 over 49. So we can use the n equals 3 case of the tower rule and calculate the probability that all aces are in different hands, use our trick to say that implies the previous event, so its probability is the same as the conjunction, and then we multiply these things and get 0.105. Okay. So I'll just say this maybe every single lecture, but try and stick in your mind the things that are highlighted in teal, and try to remember the paths by which you arrive at those teal things rather than just memorizing them by rote. Okay, so I apologize again for messing up the uploading of this lecture in the first place. Hopefully it doesn't cause you too much inconvenience that you weren't able to watch it during the normal class time.